Uniform motion may be classified into two types of motion: uniform motion with a constant velocity and uniform motion with a constant acceleration. In this presentation, we're going to demonstrate the uniform motion with a constant velocity. In the field, a race car is moving along the racetrack while a video camera is recording the event, and a digital clock is recording the time. All the information being obtained from the field of the displacement of the car and the time will be plotted in this graph. The displacement is measured in meters while the time is registered in seconds. The displacement in the first second will be taken of the position of the car with respect to the origin. However, the other displacement will be taken at the final position of the car with respect to the previous one. At time t equals 0, the car is located at the origin and registered displacement of 0. At the first second, where the digital clock is telling us 1 second, the first displacement 1 and this time is plotted in here, where this is the first displacement. In the second seconds, the displacement 2 is also plotted at this time t equal 2, where this is the displacement in here. At the time of 3 seconds, the third displacement is shown also in here at this time. At time t equal 4 seconds, where the car ends the race, it registered this displacement in here. As you can see here, in time intervals between 1 and 2, and between 2 and 3, and so on, the displacement are equivalent. Here we have equal displacement that corresponds to equal time intervals, and also we can draw a line from the origin that passes over the heads of the whole displacements up to the time of 4 seconds. Are we going to get this straight line? By drawing this line that passes over the head of all the arrows that represent the displacement, we should put some emphasis on this point, that each displacement here is taken with respect to the origin in the 4 points drawn here. So this displacement is actually is taken as a whole with respect to the origin. So we're going to make use of this graph in calculating the velocity. To find the average velocity, we have just finding delta t and delta x. To find delta t, simply just draw a line from the straight line and another one, similar one, right there, and then you can calculate delta t. Similarly, the corresponding one to t final is this one. If you draw this line all the way in here, another line in here, so this is delta x, so you just divide delta x over delta t. As you see, the average velocity here is obtained from the slope of the line. Well, we can as long as we have a straight line, as you know, the slope is the same. So the average velocity along this straight line is the same, whatever the time interval is. As you can see, we can use the same graph to find the instantaneous velocity by simply drawing this line, the yellow line, from the time scale at any instant, for example, at 2.5 seconds here. If you draw it up to intersect with the red line, and then here we draw a line tangent to the straight line. Of course, this line is going to be has the same slope as the red line, and then we can conclude that the instantaneous velocity is just delta x over delta t. We can conclude at the end that the instantaneous velocity obtained in here is the same as the average velocity, as long as the graph showing a straight line when you put displacement versus time. So this is the case where the uniform motion is a motion with a constant velocity. Sure.